Very good morning, Vanada. I am Suryanamurthy. I am from third year ECE, National Institute of Technology, Andhra Pradesh. Today, in this PPT, I am going to discuss Newton's method using Python. Newton's method is a iterative and constant optimization method. First of all, I am going to discuss the contents of Newton's method. First of all, I introduce the Newton's method, and I will show the types of Newton's method. And then I will derive the mathematical interpretation of Newton's method, and I will illustrate the algorithm of Newton's method, and I will show the few examples of Newton's method, and I will show the Python code of those examples, and I will plot the Python code graph of those examples, and I will show the few applications of Newton's method in this PPT. Introductions to Newton's method. Newton's method is a popular numerical method that can be used for both numerical analysis and optimization. In numerical analysis, it is used to find the root of a given function. In optimization, it is used to find the minimum or maximum of a given function. In Python, we can use a function that takes the function to be optimized, its gradient, and a starting point as input. The method involves updating the current point using the function's Hessian matrix and gradient at each step until a minimum or maximum value is found. Types of Newton's method. Newton's method can be broadly classified into two types: numerical analysis and optimization analysis. Let us discuss the mathematical interpretation of numerical analysis. First of all, I would like to explain this graph clearly. Let us consider x of k point which was present on g of x function, and then I will draw a tangent at the point x of k. It will meet x-axis at x of k plus 1 point. Now consider this point also present on the g of x function, and then draw another tangent on g of x of k plus 1 point. It also meet x-axis at another point x of k plus 2. Similarly, if we iterate this procedure, we will approximately reach to the root of the function. Newton's method can also be viewed as a way to derive the first derivative of f to 0. Indeed, if we set g of x equals to f of x, then we obtain a formula for iterative solution of the equation. G of x equals to 0. X of k plus 1 equals to x of k minus g of x of k by g dash of x of k. In other words, we can use Newton's method for zero finding. Simply, we have to find roots of a polynomial. Let's discuss the mathematical interpretation of the optimization for single variable case. Newton's optimization method is an iterative algorithm for optimizing a function by finding its minimum or maximum. It is obtained on the second order Taylor series approximation of the function around a point. F of x is approximately equals to f of x naught plus f of x naught into x minus x naught plus half into f double dash of x naught x minus x naught whole square. Here f dash of x naught and f double dash of x naught are the first and second derivatives of f of x evaluated at x naught. The minimum of this approximation occurs at x1 equals to x naught minus f dash of x naught by f double dash of x naught. Let us discuss the mathematical interpretation of optimization analysis in a multivariable case. Newton's optimization method can also be extended to the multivariable case where we want to optimize a function f of x1, x2 and so on xn with respect to multivariable case. This is a Taylor series expansion in multivariable case. Sorry, I will erase this one. This is the Taylor series expansion in a multivariable case. And then derivate this Taylor series expansion, and then I will equal the derivative to the 0. And then this is a continuation of the previous slide. And finally, we get x of k plus 1 equals to x of k minus gradient of f of xk by Hessian of f of xk. Algorithm for numerical analysis. First step, define the function and derivative, and then choose any initial guess for the root or optimization. Use a loop to update the current position using the Newton's formula until the desired level of accuracy is reached. Return the final approximate root or the minimum or maximum value of the function. Optimize the implementation using numerical libraries or other techniques for better performance and accuracy. Algorithm for optimal analysis in a single variable case. This algorithm also same as the previous slide algorithm. Then that's why we'll skip this slide. In a multi-variable case, define the function that you want to optimize along with its gradient and Hessian matrix. Initialize the starting point of optimization algorithm. Set a tolerance level, which will be used to terminate the optimization algorithm. Once the chance, sorry, once the change in the optimization function falls below the tolerance, define the maximum number of iterations that the optimization algorithm will run for. Implement the Newton's optimization algorithm by iteration until the convergence criteria. Tolerance or maximum number of iterations is this is the problem statement for numerical analysis. We apply Newton's method to improve first approximation x naught equals to 12. Find the roots of the polynomial f(x) equals to x cube minus 12.2 x squared plus 7.45 x plus 42 equals to 0. Here first I will derivate this function and then perform two iterations for that function using the same formula and already shown that formula in the mathematical interpretation of numerical analysis. Problem statement for Newton's optimization is single variable case. Given f of x equals to half x squared minus sin x, we have to find the minimizer of this function. Given x naught equals 0.5 and the epsilon tolerance equals to 10 power minus 6. First of all, we will find the first and second derivatives of the function and we will apply the same formula which was shown in the mathematical interpretation of Newton's optimization in single variable case. And then we will iterate that function up to the x of 4 which is equals to 0.7390. Here we will see that the x of 4 and x of 3 have same values, so the tolerance here is less than 10 power minus 6, so we will stop at here. Problem statement for Newton's optimization in multivariable case. Given a function f of x equals to 4x1 square plus x2 square minus 2x minus 2, we have to find the minimization of this function. Given initial value it is equals to 1 1 and tolerance epsilon equals to 10 power minus 6. First of all, we have to find the gradient agent of this matrix and then we will find the inverse of that the Hessian matrix and then we will find the next point by using the same formula which was shown in the mathematical interpretation of Newton's optimization in a multivariable case. Python code for numerical analysis. First of all, we define the Newton's method function. In this function, I will explain to you very easily. After finding first point of x1 using f of x naught and f dash of x naught, I already shown that formula in the mathematical interpretation of numerical analysis. Once see that formula, after finding x1, we will find the difference between the x1 and x0. If the difference between the x1 and x0 is less than tolerance, we'll stop at that x1 point. Or else we have to, if x1 minus x0 value is greater than epsilon, we move to the next iteration. This is the final object of that function. This is the taken function f of x, which is equals to x cube plus 5x square plus 2, and derivative of the function is 3x square plus 10x. After calling the Newton's method function, we get the output minus 5.077574223249291. Python code for Newton's optimization in a single variable case. Here taken function is 0.5x square minus sin x. The derivative of that function is x minus cos x, and the double derivative of the function is 1 plus sin x. Initial value x naught equals to 1 and tolerance equal to 10 power minus 6. This code are the same as limit analysis code, but here formula x1 equals to x naught minus dash of x naught by f double dash of x naught. This formula will show in the previous slide. That means mathematical interpretation of optimization in a multivariable case. So in optimization analysis in single variable case, final value x equals to 0.739085. This example is same as that already taken in the multivariable case example. The gradient are already calculated in that example, and the easy matrix also calculated in that example. Let x naught equals to 1 comma 1 and tolerance equal to 10 power minus 6. This code is same as the optimization with single variable code. In single variable case, we consider f dash of x naught, but in a multivariable case, we consider gradient of f of x naught. And similarly, in single variable case, we consider f double dash of x naught. In a multivariable case, we consider Hessian of f of x naught. Remaining procedure same as that of the optimization analysis in single variable case. The final value of that example is optimization value x equals to 0 comma 0 matrix. Python code for graph of numerical analysis. First of all, I will import matplotlib and numpy libraries, and then I will take function of x equals to x cube plus 5x cube plus 2, and then I will label x-axis and y-axis as x and y, and then I will plot x cube plus 5x square plus 2 graph. Python code for graph of optimization in a single variable case. This graph also plotted as same as of the Newton axis. Python code for graph of optimization in multivariable case. This graph also plotted as same as the numerical analysis and optimization in single variable case. Applications of Newton's method. Newton's method is used in machine learning algorithms such as arithmetic regression and support vector missions to optimize the cost function and find the optimal weights of the given model. And robotics. In robotics, Newton's method is used to optimize the motion of the robot, such as the trajectory of the robot, or to achieve the desired performance. In stock markets, also use of Newton's method. Thank you, Pulikishore sir, for giving this opportunity.